All right, everyone, welcome to today's Explainer. I'm super excited to be your guide as we tackle one of the absolute most profound yet totally everyday forces in the entire universe. Picture this. You're sitting under a tree, minding your own business, and an apple just drops right on your head. Now, look up at the moon in the sky. What if I told you the exact same invisible tether pulling that apple into the dirt is the very thing keeping the moon swinging around the Earth? Pretty wild, right? Well, today we are stepping into the classroom to take a step-by-step journey from those grounded, terrestrial apples all the way up to cosmic mechanics.
Okay, let's dive right into our lesson plan for today. We are going to start off with the history of cosmic models, then we'll unpack Kepler and Newton's laws. After that, we'll bring it back down to gravity on planet Earth, explore gravitational energy and how to actually escape it, and then decode the mechanics of orbits. And definitely stick around until the end because we'll be wrapping the whole thing up with a final exam review to really lock in everything we've covered.
Starting off with Section 1, the history of cosmic models, where we map out the heavens.
You know, long before we had fancy equations, we literally just had our eyes. Let's look at how human observation chronologically shaped our understanding of the cosmos over thousands of years. Take a look at this timeline. About 2,000 years ago, Ptolemy proposed the geocentric model. He put Earth firmly at the center of the universe, surrounded by these incredibly complex, interlocking circles. It kind of made sense at the time, right? But then in 1543, Copernicus, building on ideas from early astronomers like Aryabhata, pushed the heliocentric model, realizing, hey, the sun is actually at the center. Then you have Tycho Brahe, who basically spent his whole life just looking up and collecting raw, naked-eye empirical data. Johannes Kepler later took Brahe's massive data set and extracted 3 totally elegant mathematical ellipses. And this giant relay race of data collection finally culminated in 1687 when Isaac Newton realized something absolutely monumental. The force pulling an object to the ground is the exact same force holding celestial bodies in orbit.
Moving right along to Section 2, Kepler and Newton's laws, the actual rules of the universe.
Now that we have the historical context down, let's transition from just gazing at the stars to the specific mathematical rules that actually govern how planets move. Johannes Kepler gave us the kinematics of the solar system, describing the how of planetary motion. He established 3 major laws. First, the law of orbits. Planets do not move in perfect circles. Actually, scratch that. They move in elliptical orbits with the sun situated right at one of the focal points. Second is the law of areas. Imagine a line joining a planet to the sun. That line sweeps out equal areas in equal amounts of time. Basically, planets whip around a lot faster when they get closer to the sun. And third, the law of periods. The square of a planet's orbital time period is strictly proportional to the cube of its semi-major axis. It's just this incredibly beautiful mathematical rhythm.
Okay, so that's how they move, but why do they move this way? Well, that brings us to Newton's universal law of gravitation. Let's define this super clearly so we have a solid conceptual anchor moving forward. Every single body in the universe attracts every other body with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Put simply, mass attracts mass, and the further apart those masses get, that attraction weakens very rapidly.
And this, right here, brilliantly illustrates exactly what Newton meant. The master equation. Force equals big G times mass 1 times mass 2, all divided by r squared. It is so elegant. But here is a crazy little historical detail. Newton didn't actually know the numerical value of G, the gravitational constant. He just knew it existed. That calculation came over a century later in 1798, when a scientist named Henry Cavendish practically proved and measured G using a highly sensitive torsional balance. He literally measured the microscopic gravitational attraction between lead spheres in a tiny laboratory setup.
So what happens when there are more than 2 objects? I mean, we live in a pretty crowded universe. Enter superposition. The principle here is that gravitational forces act completely independently of one another. The total gravitational force on any single mass is just the strict vector sum of all the individual independent forces pulling on it. Every piece of matter pulls on every other piece, totally uninfluenced by anything sitting between them. You just calculate each individual pull and add the arrows up.
Let's shift to Section 3, gravity on planet Earth, bringing it back down to the surface.
Let's zoom back in from the vast cosmos straight down to Earth and see how these universal laws apply to everyday falling objects. Imagine I'm writing this out on a chalkboard for you. How do we mathematically find g, our local acceleration, when we drop something? Well, step 1. Start with Newton's universal force equation, but replace the general distances and masses with Earth's specific radius and Earth's mass. Step 2. Apply Newton's second law, which you probably remember is force equals mass times acceleration, or F equals mg. Step 3. Set them equal to each other. Notice what happens here? It's a real game changer. The little m, the mass of the falling object, cancels out entirely, leaving us with little g equals big G times the mass of the Earth divided by the radius of the Earth squared. This mathematically proves that acceleration is completely independent of the falling object's mass. So yes, a heavy bowling ball and a light feather truly do fall at the exact same rate in a vacuum.
All right, class, time for a quick pop quiz. Let's test your physics intuition. What do you think happens to gravity if you are situated inside a completely hollow planet? Just imagine all that planetary mass surrounding you in every possible direction. What do you feel?
Did you guess 0? If so, spot on. Calculus actually simplifies this scenario into 2 absolute rules of spherical shells. Rule 1, the exterior. If you're outside a uniform shell, gravity acts exactly as if all of its mass were concentrated right at a single point in its geometric center. But rule 2, the interior. The gravitational force on a point mass situated anywhere inside a hollow, uniform spherical shell is strictly 0. All those poles from all the different sides perfectly cancel each other out. No gravity inside.
So, knowing those shell rules, let's compare what happens when you go way up into the sky versus digging way down into the Earth. Item 1, gravity at altitude. As you go higher up, gravity decreases via that inverse square law because you're moving further away from Earth's center. Makes sense. Item 2, gravity at depth. If you dig a super deep hole, gravity decreases linearly. Why? Well, because of that exact shell rule we just learned. As you dig down, the outer shells of the Earth above you mathematically cancel out. So the big takeaway here is this. Acceleration due to gravity is at its absolute maximum precisely on the surface of the Earth. Whether you go up or whether you dig down, it gets weaker.
All right, Section 4, Gravitational Energy and Escape, Breaking the Tether.
Now, let's pivot from forces over to energy. What is mathematically required to completely leave a planet behind? Notice how we can visualize gravity as a literal physical pit. Because gravity is strictly an attractive force, moving an object away naturally requires you to do work. Therefore, any object bound within a gravitational system inherently possesses negative potential energy. You are mathematically stuck down in a negative potential energy well. And by convention in physics, we set gravitational potential energy to 0 only when you are an infinite distance away.
To break that tether, your initial kinetic energy from a launch has to be massive enough to overcome that negative potential energy well. The magic threshold here is that your total energy must be greater than or equal to 0. That is your escape speed. Down here on Earth, that number is huge, about 11.2 kilometers per second. But on the Moon, it's only 2.3 kilometers per second. And this low escape velocity perfectly explains why the Moon has no atmosphere. Gas molecules get heated up by the Sun, easily gain enough thermal energy to hit that 2.3 kilometers per second, and they just drift away into space.
Section 5, the mechanics of orbits. Continuous freefall.
Let's move smoothly from completely escaping gravity to maintaining a delicate, stable balance right in the thick of it. Look at a satellite in motion. A satellite orbit isn't about defying gravity at all. It's essentially a state of continuous freefall. The satellite is moving sideways so incredibly fast that as it falls toward the Earth, the curvature of the Earth literally falls away beneath it at the exact same rate. Gravity acts as the engine of the orbit. It provides the essential centripetal force, keeping it circling instead of flying off in a straight line.
Let's break down the rigid energetic cost of staying in an orbit like this. For circular orbits, the ratios are strictly fixed. Your kinetic energy is always positive, let's call it +1 unit. Your potential energy is negative and exactly twice the magnitude, so -2 units. That means your total energy is firmly locked in at -1 unit. A bound system absolutely must run on an energy deficit. If you fire your thrusters and that total energy ever reaches 0, the orbit breaks and the satellite escapes off into infinity.
Finally, Section 6, Final Exam Review Notes, your astrodynamic toolkit. All right, students, it is time to consolidate the whole shebang into a highly useful single-page study guide. Here is your toolkit. Take a screenshot if you need to. Core constants. Big G is 6.67 times 10 to the -11, and our standard Earth gravity G is right around 9.8 meters per second squared. Our universal laws.
Newton's force equation and Kepler's law of periods. Remember your variations in G. It decreases by the inverse square at altitude, but decreases linearly with depth. We've got our cosmic thresholds for escape speed and orbit speed. And finally, energy states. A bound orbit has a negative total energy, while escaping requires a total energy greater than or equal to 0. From terrestrial depths all the way to orbital heights, the inverse square law mathematically dictates the cosmic dance.
Before I dismiss class, I want to leave you with one final, totally mind-bending thought to bridge your high school physics foundation into the crazy modern astrophysics we study today. Based on everything we just learned, what happens to the universe when gravity becomes so intensely strong in a localized area that the required escape velocity exceeds the speed of light itself? Literally, not even light can escape the tether. Well, you get a black hole. But that is an explainer for another day. Keep wondering, keep studying, and I will see you all next time.